在他的网页吗？然后在这里有一个。这就是鱼吧？对啊，真的是鱼翅吧？因为我之前点它这个。它每个都不一样。那我想你赶快看电视呀！
How is it? Everybody discuss. Really have a discussion. Still, yes? Can you get this out? Can you guys do the sheet number 8? You got a copy? Block number. Yes, yeah. Yeah. I don't want the question. Do you mean this one? Which one? You mean this one?
Yeah.
Is it this one?
Question.
Yeah.
The third part.
Third part.
Yeah. So S minus this one, and then we get another normal distribution.
Yeah, then to find the probability, is it? Yeah. To find the probability of x less than y, you need to do a standardization. Yeah. Because remember, x minus y. X minus y has the normal, because these are independent, they have the normal distribution with mu x minus mu y and variance 2 sigma squared. Okay? Now to find the probability that x is less than y, it's the same as the probability that x minus y is less than 0, then you need to do the standardization. Standardization means that you need to subtract the mean and divide by the square root of this. So you do like this, minus the mean, which is mu x mu y, and then you divide by the square root of this, yeah? And you do that on both sides. You do that on both sides, yeah. And then this will become the standard normal, yeah? And this, so this would be simply phi at mu y minus mu x divided by 2 sigma squared. Okay, this is what you will get. Yeah, so this is the probability that x is less than y. To find the MLE, you just simply replace this and this by the MLEs.
So the probability.
No, the question is to find the MLE of the probability. To find the MLE of this probability, you need to replace this by this.
Alright, yeah.
Okay? You can keep this, man. You can keep this. Yeah. Guys, can you do question 1 of sheet 8? You just send a copy of sheet 8. Do you have a copy of Steve, did you give a copy to you? Alright, just a moment. Can you sign this, please?
Which question?
Question 5 doesn't exist. Usually the right to say that they but this is example class. You should work on the. And you guys, which one are you working on? Yes, what? Can you guys go on the sheet? Yes. Yes. You have questions. Sorry. Well, this is for the standard approach. This is for the indicator function approach. So depending on the approach you take, if you want, this is okay for the standard approach, but this will be the right formula for the indicator function approach. Yeah. So in this case, this will be the first one. Yeah. Yeah. Depending on which approach you're going to take, yeah. You should still. When you use the indicator function approach, you need to have the indicator function. If you use the standard approach, you don't need the indicator function. Okay.
So the one on the standard approach.
No, I will not produce any marks. Yeah, okay. It's up to you. I mean, if you want, you can try the indicator function approach first and see if it works.
In that question, you said you want to. What?
I thought which question you wanted me to do? I thought we are doing this revision example 8 now. Anyway, which question did you want me to do? Sorry. Can you see me later tomorrow, today or not today, tomorrow? I can't do it now because I've got to go through this now. Can you see me tomorrow, please? I'll be in the office 10 to 11. Alright guys, let me show you how to do, because this hour is supposed to be for, this hour is for the sheet 8, okay? Example sheet 8. So, all right, let me show you how to do question 1. Question 1 on sheet 8. I mean, if you have more questions for the test tomorrow, you can see me after this, after 6 o'clock. I will be in my office until 7 or 8 today. I mean, tonight, I mean. So you can come to my office after this class, right? Okay, if you have more questions on the test tomorrow, okay? All right, this is, can you guys listen to this, please? So this is question 1 from sheet 8, right? You are given three observations from a Poisson distribution, and we are testing this versus this. So by the Neyman-Pearson lemma, we reject H0 if the ratio of the likelihoods at lambda equal to 1 versus divided by lambda equal to 2 is less than a constant c, right? All right, the likelihood at lambda equal to 1 is this, and this is the likelihood at lambda equal to 2 less than a constant c. Now you can see that this xi bar cancels, xi factorial cancels with xi factorial, and 1 to the power anything is also equal to 1, right? So this becomes less than a constant c, right? Are you guys with me or no? Yeah. All right, so this becomes this. Now taking this guy, let me take this guy here to the right hand side. So this becomes 2 power yeah. Now in the next step I'm going to take the log. I'm going to take the log of the left hand side and the log of the right hand side. So this is going to become okay. And in the next step I'm going to divide the left and the right hand sides by minus of log 2. Now if you divide an inequality by a minus number, the sign will change, okay? So this will become x1 plus x2 plus x3. The less than will become greater than. Okay, so this is what you will get, guys. So this is the rule for rejecting the null hypothesis according to the Neyman-Pearson lemma. Now for the sake of notation, let me call this guy here, k, right? Now the next question is how to determine how do we determine the value for k, right? So that's the next question I'm going to answer. To answer that, I'm going to use the value for alpha. Remember, alpha is the probability of type 1 error. I'm going to use the value for alpha given in the question. If you read the question, guys, it says alpha is equal to 0.1. right? So I'm going to use the value for alpha, which is given as 0.1. All right, so which is the probability that the probability of type 1 error is equal to 0.1, which is the probability of remember, type 1 error is the probability of rejecting H0 when H0 is true, which is lambda equal to 1 equal to 0.1. Okay, now let me take this outside. Okay, now we reject H0 in this example if x1 plus x2 plus x3 is greater than k. Okay, now x1 and x2, x2 and x3 are Poisson variables. There's a property of Poisson variables. If you have independent Poisson variables, then their sum is also a Poisson variable. So the sum of these three is a Poisson variable with the parameter being the sum of the lambda parameters. Sorry guys, sorry. So it's 3 lambda because each of these has parameter lambda. Right? So the sum will have parameter 3 lambda. Right? So it's greater than k. And this, alright, since lambda is 1, this guy will become Poisson with parameter 3 greater than k equal to 0.1. Now this equation you can solve for k. Okay, this can be solved for k numerically using some computer software, right? This equation. So once you solve for k, you're done. All right, basically. So the conclusion, guys, the conclusion is the following: that by NP llama, we reject H0 if, right? We reject H0 if x1 plus x2 plus x3 is greater than k, where k satisfies star, and this is star. Right, so this is the final conclusion for the question 1, right? I hope it is clear to you guys, because I know we did Neiman Pearson before the histogram, and I did only one example. So this is the second example I have done with respect to NP. Right? And we now do question 2, please. Question 2 in sheet A. I mean, if you have more questions for the test tomorrow, I'll be in my office until 8 today, 8 p.m. You can also email me at 2 o'clock in the morning if you want, or at 3 o'clock. Yeah. You only need to remember the formulas in the sheet. You remember the sheet in the website. You know that one. That's not You're right, sir. How are you? Very good today. Yeah. You're ready to go. You went to Cyprus?
Cyprus?
No.
Never not. I don't think I have visa. I think I can't go into Cyprus without visa. I don't know.
I did this in the session. Use the standard approach. Where's the set? Yeah, so it works, right? So you don't need to try it. You don't need to try it. Yeah, you get the same answer. Yeah. If the event is satisfied, it gets what we want. If the event is not satisfied, it gets what we do. That's how we define. We define it, we get the function. Depending on this case, if it is true, that's what we want. If it is false, it's the same now. What's the problem? Doesn't need to be one. I don't know. It depends on the time. I don't think I said it's one. I think it was up like this and they are like zero. Because it's a minimum. Yeah, minimum is yeah, so that means if delta is greater than this, if delta is greater than this, then this is not satisfied. And therefore it must be zero. If delta is greater than that's why you have this solid line. Meaning that if delta is greater than then it's an increasing function because it's adding up. EF and delta is an increasing function of delta. So that's why you have an increasing function to this point. And thereafter it is zero. Let me ask you question 2, sheet 8, please. Oh, yes, sir. You're right. Where did you go? Only London.
Where is Cyprus?
Cyprus? It's not in Africa, it's somewhere in Europe. It's close to Italy. You're right, sir. Yeah, any more questions? No. No? You're ready for tomorrow? Yeah, it will be easy. Yeah, it will be easy. It will be easy tomorrow. All right, guys. Shh. Let's see how we can do. Question 2, all right? Question 2, you have x1 you have a random sample from a normal distribution, right, with these parameters. and we want to test sigma equal to sigma 0 versus sigma equal to sigma 1. And does it say sigma 0 less than sigma 1, or the other way around? Which way does it say? Can you read the question, guys? What does it say? Less than? Does it say sigma 0 like this? Is that right? Okay, good. Good. All right, the first part, to do the first part of the question, you need to find the rule, all right, for rejecting the null hypothesis. So I'm going to apply the NP lemma. By the name NP as a lemma, we reject H0 if the likelihood at sigma 0 divided by the likelihood at sigma 1 is less than a constant c. Alright, so it's the same as saying, guys, that so same as saying this, right? So this is the likelihood at sigma 0, and this is the likelihood at sigma 1, right? Now, simplifying this, you see that this guy and this guy cancel out, right? So simplifying this, you get one. You get this in the top, and in the bottom you get this, right? Right. So and these two guys, I'm going to take it to the right hand side, and these two you can combine. So this will become E this is what you get. And the next step, I'm going to take the logs both sides. So I'm going to take the log in the left and the right. So that will give you half the log of the left hand side is equal to this, and the log of the right hand side is right. And in the next step, I'm gonna divide both sides by this factor here, right? So I'm going to divide the left and the right by this factor. So that will give you the sum of xi squared is greater than, and the reason why it's greater than I will explain in a minute, guys, is 2.
I'm sorry, I think it's power is
Hmm?
2.
Oh yeah, you're right. Yeah, and yeah, thank you, sir.
No problem.
Yeah, thank you. I'm feeling sleepy. Look, already. I don't know whether I will be ready. I'll be ready for tomorrow's test. Hmm? All right, this is what you get. Now the reason that this becomes greater than is because this guy here is a negative number. You can see that this is negative, right? Because this is negative because sigma 0 is less than sigma 1. So when you divide something by a negative sign, you need to change the less than to greater than, right? Right, and next step, I'm going to divide the left and the right by sigma 0 squared. So this will be all right, this is what you will get. So, and for the sake of notation, I'm gonna, because this is an ugly looking expression, for the sake of notation, let me call this some other symbol, say k, right? So what we have shown so far is that by the Neyman-Pearson lemma, we reject the null hypothesis if this guy is greater than a constant k. So that answers part 1 of question 2. Now to do part 2, provided we have time. All right. So are you guys okay with this? Or are you all right, guys? Yeah. All right. Now to do part 2 of question 2. We are told that alpha. This is 0.5. I don't have the question. Is it 0.1 or 5? 0.05. Okay, good. So the probability of type 1 error is equal to 0.05. So around now we know that type 1 error is the probability of rejecting H0 when H0 is true, that is sigma equal to sigma 0. Okay, so this is the probability that right. Now let me ask you something. I know you guys have been revising a lot for the test. What can you say about the distribution of this? What distribution will this have and why? If you look at equation 75, in the printed lecture notes, you will see that this will have the chi-square distribution with n degree of freedom. Just look at this equation, guys. It's in the printed lecture notes for you, right? You see that this has a chi-squared with n degree of freedom, right? Right, and therefore k must be the percentile of chi-squared with the probability 5% exceeding it. Remember. So that answers part 2 of question 2. Remember the way I define percentiles is like this. If this is the PDF of chi-squared, right, with n degree of freedom, then the 5%, and if this is the 5% area, then this point here is the chi-squared n comma 0.05, right? So this is the point that is exceeded with probability 5%. And that's what we were looking for here, right? Yes? You alright, guys? So that completes part 2 of question 2. Now part 3. Are you done with this? Yeah. All right. Part 3 of question 2 is like this. It goes like this. It goes question 2, part 3. We are asked to find the beta, which is the probability of type, type 2 error, right? And remember, type 2 error is the probability of accepting the null hypothesis when H1 is true, right? Okay, so this is the probability that alright, this is this, right? Okay, now what you must realize here, guys, is that sigma 0 squared is no longer the true standard deviation. The true standard deviation is sigma 1, right? Because we are conditioning on sigma being equal to sigma 1. So what you must do at this stage, you probably remember this kind of thing I did before the Easter break. You must change sigma 0 squared to sigma 1 squared, right? Because the true population variance, or the true population standard deviation, is sigma 1, not sigma 0, right? So I need to multiply by the same factor. All right. Now, in the next step, I'm going to take this guy here to the right hand side. So this will become okay, and in the next step, all right, because sigma, we are conditioning on sigma being equal to sigma 1, this guy here, by once again referring to equation 75, this one must have the chi-square distribution with n degree of freedom, once again by equation 75, right? So this becomes so we don't need the conditioning. We don't need this conditioning anymore because we have used this conditioning in this step, right? That conditional on the true sigma being equal to sigma 1. This has the chi-squared with n degree of freedom. That's it. So that completes. This is clear, or we lost? No. We did this kind of stuff before the Easter break, guys. You probably remember. Yeah. All right, guys. Now, any more questions you have on the test? I'll be in my office. You know where I am, right? Then you can ask that guy sitting downstairs. He knows where I am. I'll be in my office until 8 o'clock or 7 o'clock. Just come and see me, right? Or you can send me an email 2 or 3 o'clock in the morning. Then I'll try to answer you. Yeah. All right, sir. Yeah. You have any questions? No. All right. And you guys signed the attendance sheet. You all signed the attendance sheet. Where's the attendance sheet?
说他后面这个。
It's up to you. You don't need to do it first. It's up to you. Like you should think when you get a function will work, you can try it I was in Manchester.
Yeah, I know you was in Manchester.
Yeah.
You haven't You haven't left home. Stay here. I saw your email. Do you have home?
One year.
Great.
He goes to school.
Oh, little girl.
Yeah, she goes to school here.
Grammar school.
She's in primary school.
Oh, you should look after your children.
Yeah, I know. Yeah, I know. Anyway, have you guys filled in the UEQ yet? Have you done
I'll give you all three.
Okay, thank you. But any of you haven't done it, please do it, right? Because tomorrow, after I send you the grades, tomorrow you can do it. Or you can do it today or whenever you like. Alright guys, see you tomorrow. And if you have any questions, send me an email. Right?
Today you will be in office at
Yeah, tomorrow, yeah. Yeah, I'll be tomorrow. Yeah.
You're always in your office.
Yeah.
Is that boring to stay in a room?
No, that's not boring.
Goodbye, sir.
Bye. Bye. Just check this before I send it off. Can you come to office, please? See if I can read it now. We have finished the final version of the joint. In the budget section, the parts in there are things we still need to sign before we send it out. But I'm currently asking how much additional funding our university can fund for our joint venture. The university institute assist, not assist. Assist with any funding.
That's okay. It is a joint work.
Yeah, okay. Can I check on just a minute, Steve? Because I want you, can you do the step, please?
Yeah.
No, I need to go to the office first.
Okay.
Go to the office first. The lift is not working also. Nothing's just come with me.
Just give me a sec. I sent that off now, so it's done.